So it's not my pleasure to introduce Dr. Chloe Martindale at this point. I've already had a last minute change to the program, but Bristol being fantastic, we've had one of Chloe's students who's a PhD in this field tonight. So this is Ross Bowden, who's doing his PhD under Chloe. He just told me that the write-up is progressing. As all PhD writes as we go, but he's been doing his PhD in curve-based cryptography and is another sort of famous following the path of number theory in cryptography. And so it's an excellent place to sort of talk to his work and something he has to say about post-quantum cryptography. So thanks on all counts to us.
Okay, thank you, Daniel. And thank you to the organisers for allowing me to speak here at such short notice. And thank you to Chloe for sending me the slides this morning. So I have looked at them. It's not going to be complete PowerPoint karaoke. Yeah, so it should be good. And today I'm going to talk about something called post-quantum cryptography. We'll look at defining what this is, what it isn't, our progress towards it, and we'll do a bit of a case study of one particular foundation that Chloe and I both kind of specialise in. First off, what is this term, post-quantum cryptography? It's surprisingly common when we bring this up for people to think that this is the same as quantum cryptography, which actually is a very different thing. And so we'll start at the very beginning of cryptography, and we can use this to solve many problems. But the classic canonical example is of two parties, typically a sender and receiver, trying to transmit a message to each other in the presence of a possible adversary over an insecure channel. Yeah, so this is a communication channel in the presence of an adversary. It's a non-political statement. I should make this, and yeah, and there's also the possibility that this adversary is also able to modify the data that's being sent, as well as observe it and possibly store it. And so we task ourselves with trying to allow these parties to transmit this message and obtain some properties, confidentiality and integrity. Confidentiality being the idea that these parties should have reasonable confidence that the eavesdropper, depending on the threat model and their computational resources, cannot interpret the message that's being sent. And integrity is another property that we ask for, and that is the receiver, upon receiving the message from the sender, should have reasonable confidence that this is the message that the sender intended to send at the point that it sent it over the channel. And so this is a very classical setup, and all of the parties here have under our assumption, just access to classical computing resources. And post-quantum cryptography, all we're changing is, in our threat model, we're assuming that the eavesdropper now has access to quantum computing resources of some sufficiently high power, I guess. But the important thing is that these parties that are trying to exchange do not have access to quantum resources. And so that is where we would differ from something called quantum cryptography, which is a different thing. So we're really just using classical computing and classical algorithms to achieve this. And so one sort of celebrated example of achieving this outcome was the seminal work of Diffie and Hellman in the 70s. And they just used some very basic number theory to achieve this goal. And so here is the setup. Both parties, Harry and Meghan, agreed to fix a prime number, P, or specifically they fixed the group, the invertible elements of a finite field. Yeah, each party selects a number as some base point in this group, and then both parties sample a random integer in the range of the order of the group. So it's A, Megan sample B, and they keep the secret to themselves. And then they exchange these values, n to the A and n to the B, so just a modular exponentiation in this group, and then they swap this. And they're swapping this over the possibly insecure channel, so the protocol assumes that Eve now has access to these two quantities, n to the A and n to the B. And then Harry and Megan can respectively compute the quantities n to the B, which is Megan's public key, if you like, raised to the power A, which is Harry's secret key. And Megan does analysis on the other side with the two values exchanged. And they both arrive at this value S. And so in this sense, they have achieved the protocol has exceeded in that they both obtained the same shared value. And yes, so they agree on a shared secret key. And then they can, use this in some symmetric encryption scheme to exchange messages over this channel, having agreed upon the secret value. Whereas Eve has access to both public keys, n to the A and n to the B. And so why is it that we can be confident that there is some notion of confidentiality in the scheme? And that's because we believe something called the computational Diffie-Hellman problem, which is the problem of computing this value S given just these two public keys, n to the A, n to the B, is a problem that we don't know an efficient classical algorithm to solve. And so, yeah, this is very typical of cryptography in general, is that we're very good at explaining and parameterizing insecurity. We can demonstrate attacks, and we obtain security through lack of attacks on certain classes of mathematical problems. And this has been around for coming up to 50 years, and the computational Diffie-Hellman problem and the related discrete logarithm problem, we haven't found substantially better attacks. And so we're reasonably confident that this is a hard thing for classical computers to break. But not true if an eavesdropper or an adversary has access to a quantum computer. And so this is really the entire motivation of this field. And so, yeah, in I think 1994, Peter Shaw proposed his quantum algorithm that solves a variety of problems in the area of what was that? Okay, sorry. Yeah, so a variety of problems like the integer factorization problem and the discrete logarithm problem, which are all quite closely related and yeah, are all relied upon by schemes like this one. And so our threat model is changing, and we can no longer assume that this is a secure way to do key exchange in a quantum threat model. And yeah, so this is kind of what I just said in words. So yeah, a lot of asymmetric cryptography is founded on this this thing called the discrete logarithm problem, which is the problem of basically inverting this function of raising an element of fp to the power of an integer. So given this n to the b, compute p. So that's the discrete log problem. And yeah, Shaw demonstrated that this can be solved in polynomial time on a quantum computer that's sufficiently large. Yes, and this is fairly ubiquitous in asymmetric crypto. So typically, when you form a connection over a network like internet, you first perform this key exchange and then switch to a symmetric primitive in order to do the bulk of the communication. And these algorithms are less susceptible to quantum attacks. Shor's algorithm provides an exponential speed up to the solving the discrete log problem. And there are some other quantum algorithms, famously Grove's algorithm, which can be applied to a symmetric primitive. But this only provides a quadratic speed up. This can be subverted by basically doubling the problem instances of whatever scheme you're using, and then we recover the same level of security in a quantum model as we had previously in classical. This area is less of an area of concern, but asymmetric these asymmetric algorithms can't really be recovered as exponential speed up, so no amount of scaling is going to suffice. So the main goal of post-quantum cryptography is to get around this. So we can't use the discrete log problem as a foundation for asymmetric cryptography anymore. We need to come up with new mathematical problems essentially that are A, hard to solve in the presence of a quantum computer, and B, we can find ways to integrate this into cryptographic schemes. So Shor's paper came out in 1994, and quantum computers have been theorized long before that. And so we should probably, convince ourselves that this is a real threat, and that it is something we need to adapt to. And so my colleague Sam Jack has this very helpful infographic that he put on his blog in 2021, and this kind of shows the state of modern quantum computing as it is today. So typically, from an engineering perspective, we care about the size of the quantum computer measured in the number of qubits, and also how often they're prone to failure. Being a quantum mechanical system, it's quite volatile. Like passing neutrinos can disrupt these things. So we care about both the number of qubits and how prone they are to errors. And so this is what these two axes are. And then up here we have a collection of applications we think quantum computers are going to help us with. These are the more constructive ones, like protein folding and quantum chemistry and things like this. And these are the really destructive ones that we care more about as cryptographers. So this is the points where various levels of RSA are broken, for example. And then this grey square down here is kind of the state of the art, or the state of the art in 2021, and it has various corporations and institutions, quantum computers placed on it. This was in 2021. You can see we're a long way off, but hopefully he republishes this every year to update us all on yes. Yeah.
I was just wondering, because the scales are kind of exponential.
Yeah.
I was wondering, is there a claim somehow that progress is kind of constant on this exponential scale? Do you know what I mean? So should I be imagining this gray thing is going to be every year growing by a fixed amount?
Yeah, it's hard to say. It's purely an engineering problem, and
So you're asking, does Moore's law apply to quantum resources in two axes? And the answer, empirically to date, seems yes, and something a bit faster than Moore's law.
Yeah, I spoke to Jack Sam about this, and he said like every year there is a independent probability that there'll be a major advancement. So every year it's always 7 years away. But if there's no advancement, then that's when it gets pushed up. So it's quite volatile in how much progress moves, I think. But yeah, I can show you how this has evolved. So this is.
Oh, yeah. Sorry, I didn't realize you were going.
Oh yeah. So we have the next 4 years here as well. So there we go. but it's not linear. So yeah, it's a valid question. So yeah, so we can see how this grey box expanded. These models from Google and IBM, I think in their published work, they had sort of error bars for their estimates of the error rates that they had on their machines. And then yes, we also had like this advancement here. So I'm not an expert on this area, but it's not just the case that we'll find advancement in quantum computing engineering, but we might also find better ways to implement quantum circuits more efficiently, making them less error prone and thus requiring fewer qubits and fewer gates. So you can also have advancements where all of this moves down and the resources go up. And so this was then 2023, and it advanced a bit more, and then 2024, and then this is 2025, so this year. And you see the major change is that there were quite a few advancements that were combined together in this reassessment of the resources that were needed to break at various instances of RSA, and the culmination of all of those brought all these lines closer in. So yeah, we are sort of converging to a point where these problems are worryingly close to being solved. So yeah, not only is this threat advancing, but I'll say one more point is that in our threat model we also have this idea that adversaries with sufficient storage can take part in this practice of harvest now, decrypt later. And this is an idea where large bodies can just gather encrypted messages that are being sent over a network, and then at the point where they have access to quantum resources can then decrypt that traffic from many decades or years ago. And so when analyzing how much of a threat quantum computing is, we also have to take into account how long we want this data to be secure for. And so, we all, I'm sure, have messages that we expect to have privacy now and, in several decades' time. But if they're being transmitted using classical asymmetric cryptography, that assumption might not hold. So this is the motivation to transition to post-quantum crypto really as soon as possible. And so this is an outline from the NCSC, which is the UK's National Cybersecurity Centre, and this is I guess their idealised timeline for this transition to occur in the next decade. Are we ready? People have been thinking about how to solve this problem for a while, and there have been a few schools of hard problems that have been theorized for providing new mathematical foundations for asymmetric cryptography, and these are some of the more popular ones that people like, people have proposed schemes based on. So I'll go over a few of them. So code-based encryption and signatures. This is quite a classical problem of decoding random linear codes, which has applications generally in networks, but has been also used to do asymmetric cryptography as well. Hash-based signatures. So this is a means of doing signatures. So a different primitive to the message encryption that we showed earlier, the key exchange, and just using standard hash functions that we already constructed for other purposes. Isotopically based encryption and signatures. This is a bit more exotic and number theoretic, and this is based on computing certain morphisms between elliptic curves. I'll talk about that more in a second. Then we have lattice-based encryption and signatures. So there are quite a large family of problems relating to lattices, such as finding the shortest vector in a lattice given an arbitrary basis of that lattice, or the closest vector problem, and things like this. And you can build, again, encryption and signature schemes that have reductions to these studied problems in lattice theory. MPC in the head is a bit newer. This is the idea of performing a multi-party computation entirely yourself, and then committing to each party's value, and then sending that to a verifier, and they can verify that you are computing this multi-party function honestly. And multivariate signatures is based on the problem of trying to solve like many multivariate systems which are not linear but quadratic in their variables. And you can build a trapdoor from this, which you can get signatures schemes from. And in this red and green text, there's you know, sort of various pros and cons attached to each approach, which are very general. And yeah, one upshot of all of this is that we are struggling as a community to find approaches that mirror all the benefits we had in classical asymmetrical cryptography, using things like the discrete log problem. So there are always, it seems, trade-offs between speed and bandwidth and other properties that we like. So a case study. So this is the area I work on mostly of those schools, and this is a fun slide about how you can perform a key exchange with a friend if you ever find yourself bored in Manhattan. And so what you do is that you both start on the middle of Broadway, and you and your friend both take a random sequence of directions in Manhattan, and you note them down, and you both end up somewhere in the city. And then what you do is you transmit those directions to your friend that you've taken, and then they take your steps and you take theirs. And because it's Manhattan, everywhere locally it looks the same. So you can do this, it works. And the result is that you'll both end up in the same place. So yeah, it's very, very extremely classical cryptography, just talking about, yeah, it works. So so great. So you can do cryptography just given a graph. Obviously, Manhattan is a very structured graph, yeah, the problem is the analog of the discrete problem here is trivial to solve, because if I have the two endpoints of where this red arrow has started and finished, it's very easy to derive a sequence of directions that take you there. Mainly you walk X and then walk out Y. So this is not yeah, so this is not a good start, but yeah, it turns out that using these things called isogeny graphs, we can build graphs where actually we can do this style of graph-based cryptography, and it has a lot of the properties that we would need in order for us to have security. And so yeah, so some properties that we have from these graphs. I have some pictures of the graphs in a second, but firstly, as we scale our parameters, we get exponentially many vertices. Yeah, locally, we can walk very efficiently on these graphs. So just given whatever structure represents a node, we can enumerate the directions we can walk and then move to the next node easily. These are fast mixing. So I said they're exponentially sized graphs, but what we also want is that If you start from any point in the graph and you take a random walk, you want to be able to reach almost all nodes like reasonably quickly. And so, yeah, this is a fast mixing property or expanded graph property, if you like. And yeah, so the key problem in the slide before is that, given two endpoints of the path, it's very easy to derive a path between those endpoints. But in this case, just given the representation of the two vertices, actually computing a path between them is very difficult. Finally, I guess in the Manhattan structure as well, you had a very clear notion of direction wherever you were locally in the graph, so north, south, east, west. And similarly, in this case, we have some way of attaching some notion of direction when you're at an arbitrary vertex. And then, obviously you all want to see the pretty pictures, and so here they are. And so these are examples of isogeny graphs. And this is, I always think these look like a spirograph when I see them, this one a bit more chaotic. So this is an isogeny-based key exchange called Seaside. You wouldn't think it's pronounced like that, but that's what we go with. And it involves taking walks in a graph that looks like this, and then ski sign is a slightly more modern one. This is the two isogeny graph. Ski sign, yeah.
I was just wondering, there were two properties that sort of seemed intuitively almost opposite, like so the third and the fourth. So if I take any two paths, I know that there's only any two nodes. I know that there should be a short path between them.
Yeah.
But point 4 is I can't find it.
Yeah. So So if you're trying to brute force find like all possible paths of length, say n, like from a starting point, and the graph with regularity d, and you're doing something like this, d, you have to enumerate d to the n things.
So 4 is not finding just one path; it's finding all paths.
No, it's more that you don't have a way to recover the path beyond just essentially brute forcing until you find that vertex. Right. So it's a bit misleading to call it graph-based cryptography, because when you're actually doing all this, you don't have access to the graph. You just have you have an elliptic curve essentially, and so having this data doesn't tell you anything about where it's located in the graph, and so the attack is just kind of abstracting to the graph structure, and you say, okay, I start from this curve and I walk in every direction, and then see where I land. And essentially, you have no information about how far away you are until you land on the correct elliptic curve. So this is the point about recovering paths, is that having that data of the curve doesn't really tell you where you are in relation to anything else. Whereas in the Manhattan example, the only way you can represent these 2 points is with like an XY coordinates, and that's, you can clearly derive a relation between them. So what's happening here locally, which kind of relates to that, is we don't actually have access to the graph, but what these nodes are is something called an elliptic curve, which is an algebraic geometric object that kind of looks like this, and given by a polynomial equation that looks like this. And there's another one here, and these are connected by something called an isogeny. And an isogeny is just a morphism between elliptic curves, which is given by rational polynomial functions, and is also a homomorphism for groups. So this is a free isogeny in this graph, and I think these green and red ones are 5 and 7 in this instance. So the degree, the prefix of the number is something called the degree of the isogeny, and this is in the simplest terms, it's just the degree of the polynomials that appear in the description of the rational function. and kind of measures the complexity of traversing that edge. And yeah, so I said you could do an analogous thing as you did in Manhattan, and here it is. Like before, you fix a starting point, and Alice and Bob, in this case, choose a sequence of directions. And so Alice walks in the negative step twice on the blue subgraph or the 3 isogeny graph, and then takes positive direction in the 5 isogeny graph or red, and then Alice takes one more positive step in the 7 isogeny graph or the green edge. And Bob does a similar thing. And the point is when they each transmit the directions, just the directions, and the just the directions to the other party, and not where they are, then you compose these 2 walks, and they both end up at the same place, like Manhattan. And so if you're building a key exchange from this, then these amount to the sorry, you don't send the directions, you send the point you're at, and then they redo their own walk. So these amount to the secret key, and then the actual points on the graph are the public key. And yeah, like this alluded to, the graph abstraction is very nice, but what's really going on under the hood is you're computing a lot of these functions and point calculations and things like this. So you're doing a lot of coloring with the graph abstraction as well.
Can I ask something about directions?
Yeah, sure.
So in this case, what I really know, you have only 2 directions that you can go to.
Yeah.
Say that you have 3. So in that case, how would you define direction?
Yeah, it's a little bit technical. So these functions have kernels because the elliptic curve groups. And then you can it suffices to generate an isogeny just by its kernel, and you can have different isogenies with the same kernel, but they lead to isomorphic curves, and you only care about the isomorphism class of the curve. So you can just look at kernels, and then it's a theorem that each curve should have one FP rational horizontal isogeny, and then one FP squared, but not FP rational isogeny. And this is how you assign the directions to these. So yeah, one direction is the FP rational one is the FP squared rational direction. So yeah, this comes back to the point here about being able to attach some well-laid meaningful direction. So this is one example, and this is kind of the flavor of post-quantum cryptography that I work on, and it's one of the candidate foundations for post-quantum cryptography. And so what are its pros and cons? Typically, T-side among other isogeny-based streams, they benefit from having very small bandwidth. So the public and private keys are very, very short and compact, which is something we've struggled to obtain with other post-quantum foundations like lattices and codes, which involve a lot of very large high-dimensional matrices. So we're taking up a lot of bandwidth to be. But because there's a lot of sort of advanced algebraic geometry happening under the hood, these are quite slow. So the computations involved just to traverse one step in that graph I showed is quite a substantial amount of polynomial arithmetic. This is like 1,000 times slower than performing like an elliptic curve if you have a key exchange. So that's not ideal. And with a lot of these things, you know, post-quantum cryptography is relatively new as a field. I said earlier that we've had sort of 50 years to cryptanalyze the discrete log problem. We've had very little time to cryptanalyze this isogeny problem or many other problems that we're hoping to base post-quantum cryptography on. And so it doesn't enact a huge amount of confidence in basing a lot of this on schemes that are only a few years old. Yeah, it also facilitates something called a non-interactive key exchange, which is an example that we did in Manhattan or at the very beginning with Diffie-Hellman, but actually it's the only post-quantum foundation we know that we can really do this efficiently with. And this is used a lot in things like the signal protocol, the TLS, and so it's the only thing we can really use to have a drop-in replacement in those schemes.
So, sorry, I missed this. In the Seaside protocol, what is it that the eavesdropper doesn't have that?
So the information they send is just the node they end up at. Yeah. So these arrows. So the directions are secret.
Mm-hmm.
So Alice would take this walk and then just send something representing this elliptic curve to this node to the other party. And that suffices because then, Bob repeats his walk from that node. The node is the data of an elliptic curve, which you can represent with coefficients of J.
If I could just phrase this slightly more abstract, I've got a very different background, so I'm just trying to rephrase this in a different sense. So what you've got is an implicit graph, which is your isogenies. And then you communicate in the open a starting point in this implicit graph. And then as a secret key, you take a collection of directions to move. So you and I each have those. I start from the starting point, I end up at some point and I deliver that to you. You deliver yours to me. And then I apply my path to the point that you ended up in. And so the two features that this graph has to have is that deducing the path from the endpoints is difficult. And that the application of the directions commutes.
The commutativity is a part I haven't mentioned.
That's a critical point here because the directions are implicit and cannot be derived from the locations.
Indeed. This is This is also an important property of this graph and the Seaside graph as well, is that there is some commutativity and so it's really a group action and it's enacted by a commutative group, and then we do A then B, that's the same as B. And that is not true in something like Seaside, but there is other information. That's where you require other information in order to be able to resolve that.
So having something like a free graph with a very small number of identities on it would give you something that's very close to it. Okay.
And if anyone recalls SIDH, which was one of the first isogeny-based schemes where that was broken a few years ago. There they work in a graph where they don't have this commutativity, so they have to include extra information when they send their endpoints. And it turns out this information was sufficient to make it. This is just a bit about the non-interactive key exchange that I said about. So, we use this property of being non-interactive in a lot of low-level primitives like TLS, which secures web traffic, and the signal protocol, which is used in a lot of group messaging settings as well. Substituting this for something that isn't a non-interactive key exchange is tricky. So this is a good selling point of Seaside, despite it being very slow. Okay, so where are we up to now in 2025? And so one initiative, if you like, that has helped spur research and cryptanalysis in this direction was the announcement, I think, in 2016 of the NOTA competition from the US organization NIST, the standardization arm of the federal government, if you like. And they, opened for a call for people, research groups and whoever to submit candidate schemes for post-quantum key exchange protocols and also digital signatures. And this has been going on for the past decade, and it had some form of conclusion a few years ago, where two key exchange protocols were selected to be standardized, namely Crystal's Kyber, which is a lattice-based scheme, and H2C, which is a code-based scheme, and two signature finalists as well, Crystal's Dilithium, Falcon, and Sphinx Plus here. And yeah, so this competition ran by having several rounds where the community and in-house cryptographers at NIST would analyze these schemes and apply some metrics like speed, performance, ease of implementation, openness to side channel attacks, all sorts of things to try and sieve out what would make a good replacement scheme for a lot of for pre-quantum these pre-quantum primitives. And additionally, it gave the community a lot of opportunities to try and break stuff. And that's kind of what happened. And so, yeah, a lot of, I think the very first round, it was of the order of 60, 80, maybe key exchange candidates, and a lot fell by the wayside for being broken, things like this. And not just like in the early stages of the competition, but actually several candidate schemes made it quite far. And indeed, we're almost about to be finalized, for example, like Psych, before it was catastrophically broken. So I don't know how much confidence this installs in our quest for post-quantum cryptography, but it really goes to show like how immature all of this foundational stuff is in the grand scheme of things. Yeah, so this is a kind of a report of some of the attacks that happened since this competition start. And so there was a scheme, I don't think it was listed here, called but it made it to the third round, I think, so one before the fourth round, called Rainbow, and this was based on some multivariate quadratic. It had its foundation multivariate quadratic equations, and Wild Bullens, a colleague at Zurich, I think at the time, or IBM, famously about this paper called "Breaking Rainbow Takes a Weekend on a Laptop," and there was this proposed attack on this scheme, and he optimized it and ran it over a weekend, and broke what should have been the equivalent of breaking 128-bit AES. So this is obviously not fulfilling the security requirements that are claimed. This was also quite funny in the aftermath, in that this signature scheme had been integrated into a certain cryptocurrency called ABC Mint, and I think the inventor of not the inventor, but a prominent proponent of this cryptocurrency had offered a bounty or something for people trying to sign or forge a message based on some address on the chain, and yeah, offered a lot, like I think $400,000 or something.
I think they actually offered cryptocurrency.
It might have been $400,000 in cryptocurrency, or maybe this cryptocurrency, which, as you can probably expect, is now not worth very much when they published this attack. But yeah, so this also shows the dangers of trying to integrate any of this stuff without going through the due process that NIST and other organizations are trying to do. Back on lithology-based cryptography, also in 2022, there was this sort of week of subsequent papers that found this attack on SIDH or Psych that was previously unknown, and uses genus 2 arithmetic to attack genus 1, the genus 1 key exchange. And I think the optimized version of this attack you can run in like milliseconds, and this is again something that's meant to achieve sort of the same level of security of 128-bit AES. So this goes to show how immature a lot of these schemes are, and we should be placing a lot of confidence in them yet, and a lot more resource is needed to analyze these schemes. There is also, some ongoing work by Daniel Bernstein and Tanya Langer, who are exploring a research program on whether there are ways to exploit the number theoretic structure in a lot of lattice-based schemes. So a lot of lattice-based heuristics rely on sort of assumptions about unstructured or random lattices, whereas the lattices we use in a lot of lattice-based cryptography rise from rings of integers of number fields, where there is a lot of arithmetic structure that you can exploit both to speed up the use, speed up the algorithms, but also potentially leads to additional attack avenues. And so, given that already we've had a few schemes that are based on these structured lattices, it is at least concerning to hear the noises of this, even if they are quite contested. So that's kind of where we are. And yeah, this kind of sums up, various things that I've aired about, like what needs to be doing, and we have a lot of proposed candidate schemes, and we have a lot of proposed solutions to some cryptographic primitives. But like I said at the start, sending messages and signatures is the very first thing you want to do in crypto, but actually there are a lot more interesting and exotic protocols that we would like to have close quantum analogs of. Maybe things like delay encryption or e-voting schemes or threshold schemes, things like this. These are more advanced, and the work needs to be done to also find post-quantum analogs of this for the future. And yeah, other things. So more cryptanalysis, obviously, given in the context of what we talked about and how many things have been broken. And finally, just theorizing and specifying these algorithms is the very first step. But I think, to actually have them widely deployed, we need sort of dedicated teams to instantiate implementations of these on specific hardware, site processes, and dedicated instruction things. And this is still a long way off, given that we're only just beginning to actually produce the specifications of these schemes. So there is a long way to go still. I think that's all. Thank you very much. And
are there any questions for us?
Given the complexity of the maths goes up here quite considerably from the early days of public key, given that people failed to implement either in software or hardware, those first waves of public key, what confidence do you have in the likelihood of people being able to do the engineering to support this? Because the number of people or the number of companies capable of doing it is going to decrease.
Yeah. There's a lot of, there's a very like something like there. So there's this something like ski sign here, for example, uses a lot of like arithmetic from quaternion algebras and also high dimensional algebraic geometry. So you have to know a lot of things, a lot of mathematics, just to be able to even understand the protocol in theory. And so asking the average even cryptographic engineer to understand all this stuff is a high bar. And so I think we need to place a lot more confidence and resources in basically these standardization bodies, and so that people can have the confidence that they don't need to know this stuff and know all the details. And yeah, we shouldn't be leaving it up to lone developers or companies to do this.
Yeah, and I had a question about, basically the basic setup. It wasn't clear to me. I get the Manhattan example.
Yeah.
I just, how is this useful if you see what I mean to send a message?
So this is a key exchange. So the idea of a key exchange is not to, so maybe I skipped over this, but it's you derive some shared secrets for which you can then do symmetric cryptography.
Right. So the final location we've arrived at, that's a shared secret.
Yeah. Because in principle you cannot control this endpoint that you're going to take. So that's not practical for sending a message, but it's a thing you can be confident that you two both know and nobody else does. And then you can use
then we can do something else.
Exactly. Yeah. So
So one of the disadvantages of CSAT that you didn't mention is that there's been some interesting quantum cryptanalysis in the form of Piket's she solves CSAs on the C side.
Yes, yeah.
Which isn't exponentially fast like Shaw, but isn't quadratically slow like Grover.
Yeah.
Does that not sort of take a little bit out of the sort of reckoning from your point of view?
No, indeed. I think also one problem with C-side, is in order to overcome that sort of sub-exponential attack, which is in a sort of grey area of like RSA, I guess, in that, the parameters scale badly. And so, it's in a grey area in that sense. And also, we're like in that attack also suffers from, same sort of phenomena that goes on here, that so much of the analysis depends on like really technical like details of how you arrange the circuit in the quantum computer and things like this. So evaluating the security of things that have sub-exponential attacks is also very tricky. So C-side's pro is that it is that only post-quantum non-interactive key exchange, but it does have a dubious security standing in a post-quantum setting.
Should we thank speak again?